My name's Taylor Robnett, and I'm in Group 4, lead for the air conditioner experiment. So for this experiment, we're going to use a heat pump, and we're going to do a thermodynamic analysis of a heat pump at different charges of Freon. So most of you might not know what a heat pump looks like, but this is what it looks like. This is a typical heat pump. It's purely just an AC unit. This is actually what it looks like, sliced in half. The components are actually a little bit more complex in this cycle, but I do know that that's the compressor. And this is actually a simplified cycle that we're going to go through. First, our Freon is actually going to start over here. We're going to compress it here. So this is state 1. We're going to compress it. State 2 will come out of the compressor and then into the condenser. And once it's leaving the condenser, we'll have a high temperature. And then once we get out of that, we'll go to our expansion valve, which is our capillary tubes. Then we'll go straight from there to the evaporator. Now it'll give us our low temperature of the cycle. So like I said before, we're going to use a heat pump and do a thermodynamic analysis of the heat pump. And we're actually going to look at the coefficient of performance. We're going to take readings at 14, 14.5, 15, 15.5, 16, 16.6, and 17 pounds of Freon charge. I think it's Freon 22R. So the theory behind the whole coefficient of performance is basically what you're putting in and what you're getting out. In this case, what we're putting in is electric energy, and what we're getting out is heating or cooling. So as lead, I was asked to determine what our COP was for 500 and 1200 kPa. The 500 would be coming out of the evaporator, and the 1200 would be coming out of the condenser. And we needed to use the steam cables to calculate the COP. So coefficient of performance is given by T high over the difference of T high over T low. T high is the gas leaving the evaporator, and T low is the liquid leaving the condenser. So here's a table of the saturation table for Freon, the Freon that we're using. And so we need to interpolate to find these values. There you go. So for T low, our interpolation yield that T low is going to be 273.3 roughly Kelvin. And then for the T high, our calculations will yield about 303 Kelvin. So now when we plug this in, we get a COP of about 10.06. This is our ideal TS diagram for the refrigeration cycle. We're going to start here, and we're going to move our way up. This is actually the compressor we're putting work in. So this is a side-by-side, if you'll follow it. So we're going to start here. We're going to compress the Freon, putting work in. And then we're going to bring it back down. We're going to compress it to this superheated vapor. Condense it back down into a saturated vapor, into the vapor dome, bring it across to where it reaches a saturated liquid. Then we're going to basically put it through an expansion valve or a capillary tube. It's going to bring us down into some region in the vapor dome. And then we're going to evaporate it back over into a saturated vapor. And then we'll repeat the process over. So here's the pressure and enthalpy chart. And we're pretty much going to go through the same thing. We'll compress it here. We're going to add energy. And then we're going to condense it. And we have no loss of energy here. We're basically just, or I'm sorry, we are actually losing energy. When we condense it down into a liquid. And now here we're not losing any energy, but we're decreasing the pressure. And then here we're actually gaining energy. So the heat pump can be used as an effective air conditioning unit or device. In this case, we don't really expect it to be that efficient because there are, for what we did, for the calculations, it would be extremely ideal. We're not counting leaks or, the efficiencies of the heat pump.